So to make this ocean warming patterns a little bit clearer, let's go through a few regions one by one to understand what is the region-specific dynamics that determines its own warming rates, right? And what better place to start than in the Arctic, because you have probably been hearing a lot about the Arctic, its warming, sea ice loss, even a complete opening of the so-called Northwest Passage, where if the sea ice becomes so thin that you can directly cross from the North Atlantic into the North Pacific Ocean through the Arctic Ocean. Remember, the sea ice is blocking that pathway. But during some summers, so the sea ice wants to build in the winter months. The spring, summer months, the sea ice begins to melt at the edges and contract. And in some summers, September is when kind of the maximum melting happens. In some couple of summers, it has been so open that one could cross directly across. That's not good news, by the way. Okay, so here is the Arctic amplification we will talk about later, but look at the trend in the extent of the sea ice. Okay, so there is sea ice extent, which is basically seen as the area over which you have some ice present, or you can calculate the area of sea ice by accounting for the holes. So sea ice is like Swiss cheese. It has a lot of holes in the middle. So you can actually try to calculate the area as opposed to the extent. So here 30-year average extent was this far, and in 2012, August 26, you can see how many million square kilometers of sea ice has been lost over time. So here you are showing the extent in million square kilometers from 1978, where we have good records. There are past records recreated by naval data from Russia and other countries, which was made open after some declassification. So you can see that there is year-to-year variability. As always, there is internal variability or natural variability, which changes from year to year, the extent of the ice, but there is an unmistakable downward trend in the Arctic sea ice extent. What is happening here? Albedo, ice albedo feedback, right? So if you melt sea ice, you're going to reduce the albedo, absorb more shortwave energy during the spring, summer months. It only gets 3 months of sunlight beyond the Arctic Circle. That is going to increase the heat content and melt more ice, make it warmer, reduce the albedo and so on. But the Arctic also has a very peculiar circulation, which can bring in warmer waters from outside under the ice and melt it. Okay, remember, ice is a very good insulator. So if there is ice, ocean cannot lose heat to the atmosphere. But if you're bringing warm water below and melting it from below, then obviously this insulation is not so important in that case, right? So loss of more than 2 million square kilometers or 800,000 square miles of Arctic ice in just the last decade. So enhanced warming, so that's where the polar amplification or more warming at high latitudes comes from. Arctic ice melting obviously affects people who live there, like the Inuits, and species that live there, like the polar bear, the top predator, apex predator. They rely on ice for wandering around and finding the holes and grabbing the seals or other fish and so on in the waters. That's the way they live. They hibernate through the winter and come out in the spring and try to go around hunting. Obviously, polar bears have been used as a poster child for climate change, but as it turns out, people kind of get desensitized after seeing the image for a while, especially if it's something that's happening far away and if they don't know exactly what they can do about it. Okay, so minimum in the summer of 2020, the Arctic ice reached its second lowest extent on record. Okay, so the median extent for 81 to 2010 is again shown with this line outside, and you can see that there is the other factor called sea ice concentration. So these blue edges is where the ice has gotten thin, and where you have these white colors, the ice concentration is 100%, that it is really frozen ice. Okay, remember we cannot form very thick sea ice because it sets up brine rejection and circulation, which brings more heat and so on. But the Arctic is almost closed like a lake, and it is very fresh because of all the snow melt and rivers coming in, which makes it easier to freeze, right? Salt reduces the freezing temperature. If it's fresher, it'll freeze easier. So look at this time series here for 2020. As we said, this is showing many years, 2020, 19, 18, and then the median of the long term. You can see 2020 is this blue color here. 2012 was the lowest extent, and 2020 is heading to be the second lowest sea ice extent in the Arctic. So the circulation looks like this. As we said, there is a North Atlantic current coming all the way into the Arctic, and it's a warm current. And then there are transpolar currents, which are the deeper cold currents. There is a Bering Strait exchange on the other side. It's just about 1 Sverdrup, which is what? 1 million cubic meters per second, 10 to the 6 cubic meters per second. We measure transports in Sverdrups, and for reference we said the Amazon carries 0.2 Sverdrup, so 1 Sverdrup is a lot, right? So there are these kind of gyres, Beaufort gyre and Norwegian seas here. So there are complicated circulations, and these currents that go out tend to take out the sea ice, chunks of sea ice, or glaciers carving off of Greenland, icebergs floating down deep into the North Atlantic, which caused the Titanic accident, for example. So the circulation is complicated. Ocean is warming, bringing more ocean warm waters into the Arctic and melting the sea ice. So it's getting hammered by surface warming as well as warming of the ocean. And there is also a cloud feedback in addition to the ice albedo feedback. Arctic, it turns out, has lots of clouds, and the warming and the increasing water vapor is also providing some feedback from cloud buildup and the radiation balance. Complicated, right? But one thing is clear, we are losing sea ice.